to present today, and we are all very excited. And yes, the floor is to you. Please start.
Thank you so much, y'all, for having me here. And it's awesome. I'll just start sharing the screen. Is it visible?
Yeah.
Okay.
Yes, we can see it.
Is the entire screen visible or like only a part of it? Because I cannot see the entire screen.
Entire screen is visible. Yeah.
Okay. Okay. So, hi everyone. My name is Bharti, and I am a master's student studying at Osmania University, Hyderabad, India. And today we'll be speaking about correlations, just the fundamental elements of correlation. Okay, so we will start with an experiment that was conducted by Sir Francis Galton. He was the cousin brother of Charles Darwin. Inspired by what Darwin was doing, Francis started studying the inheritance of stature. Stature is the height. So, to study the inheritance of stature, Galton started by collecting the observations and families consisting of parents with grown children. So, to calculate, he started calculating by, the mid-parent height as the mean of mother's and father's height versus the offspring's height. And then he concluded that taller parents generally, but not inevitably, produced offsprings who were relatively taller. I cannot see the entire screen. I'm so sorry. Can I just stop share and share it again?
Yeah, sure. If you want, you can just keep it like the slides visible. You don't necessarily have to.
Okay. Oh yeah, I think that's a much better one. Okay, is it visible?
Yes, it is.
Awesome. Okay. So here we have two variables. One is the mid-parent height, and the other one is the adult's offspring height. And these, all these entries are known as cells. And so the reason why I'm showing you this particular chart is because I want to say that correlation is usually between two variables, and the relationship between these two variables are known as bivariate distributions. And also, don't worry about this line. Galton just wanted to, see the medians of all these data sets for all these columns. And he, observed that there's a straight line as a pattern. Right. So now, what is correlation? In the most simplest terms, correlation is a measure of the degree of relationship between two variables. We will discuss more on what are the trends of correlation and what are the conditions of correlation, but I just wanted to say that this is what all correlation is, the measure of the degree of relationship between any two variables. There might be few conditions such that how the variables are measured, continuous variables or discrete variables. So we'll talk about that in the later stages. Also, if anyone has a doubt, you can just unmute and ask. I don't know where to stop and ask for if there's any doubt. Yeah, you can just unmute and ask. Before we start talking more about correlations, we have to talk about scatter plots because they're awesome and they're very necessary. All right, and before we start just diving in and going wild, working out with the correlations, it's important to put your data in a scatter plot and look at the trends. How is the data? So correlations work only for linear relationships. So we can just like look how is the linearity of the data, and are there any patterns exhibited by the data. You can also like look for any potential outliers of your data set. And yeah, you can also see the strength of the relationship between two variables. You can also see if it's like the data is has an increasing or a decreasing pattern, or is it positive or negative. And one thing that we can see is that the more the scatter is of the data, it just means that uh, the correlation is that much weaker. mm, okay, so there's this thing called directions, and this is only for linear relationships, right? Correlation is only for linear relationships. There are mostly three types in the broadest classification possible. One is a positive correlation, which is denoted by plus sign, and then the other one is a negative correlation, which is denoted by minus, and then the last one is that there's no correlation, which is near zero. So positive correlation says that as a variable increases, the other variable also increase, right? And then the negative correlation says that as a variable increases, the other variable would decrease. And no correlation does not mean that there's no relationship between the two variables. It just means that there's no linear relationship between these two variables. And there's also a possibility that change in one variable might not result in the change of another variable by a predictable value. Yeah, so no correlation does not mean that there's no relationship. It just means that there's no um, linear relationship between the two variables. Have depicting strong positive correlation, a moderate positive correlation, and a weak positive correlation. So you can see that in strong positive correlation, the data sets are more close to each other, and you can see the trend very clearly. In a moderate positive correlation, the data are more scattered and than compared to the strong positive correlation. And again, in the weak positive correlation, the data is even more clustered and scattered. And you can see the same thing in strong negative correlation. And the moderate negative correlation is more a bit scattered compared to the strong negative correlation. And the weak negative correlation, the data is even more scattered compared to the rest of the two. You could probably like check this out more in detail. I'll share the PPT afterwards. So these are the conditions of correlation. I'll not be reading these out loud right now because we could probably go in detail for each of the point. So the first point is that correlation is applicable only to linear relationships, as we discussed before. So, it just means that the relationship between the two variables will remain same, throughout their range of values. If a variable increases or decreases, the other variable also changes by a predictable value. So, for example, we could probably discuss about the relationship between the number of hours worked and the amount of money earned, right? So as the number of hours worked increases, the amount of money earned also increases proportionally, assuming that there's a constant hourly rate. Again, this is if there's no exploitation. And the second one is that it provides direction and strength. So this is one difference that I have when compared to covariance, because in covariance it just talks about the direction of the relationship between two variables, whereas correlation also talks about the strength. um, yeah, direction just says if the variables have a positively related or negatively related relationships, while strength talks about how closely the variables are related to each other, right? So let's say that, if you're interested in studying the relationship between hours of sleep and academic performance in college students, uh, what do you think a positive correlation would look like between these two variables? If anyone wants to answer, they can just like unmute and say,
So maybe the increase in number of hours of sleep will lead to better academic performance in college students.
yeah. And what about a negative correlation? If it's like if we apply the same thing to these two variables from the perspective of a negative correlation, what do you think the statement would look like?
So the more they sleep, the poorer their academic performance would be.
Yes. And also we have to note that positive does not mean more stronger and negative does not mean more weaker. It just means, I'll explain that in the coming slides. The next condition is probably something that we have heard a lot, we have read a lot, if even if you're studying intro to statistics, where there's anything written about correlation, that correlation is not causation. So like, even if two variables are correlated strongly to each other, it does not mean that one variable is causing the to affect another variable. We can probably take the example of ice cream sales and crime rates. So they might be highly correlated during the summer months, right? But it does not mean that eating ice cream causes an increase in crime. So there might be other factors that come into play that which influence these two variables. So because it's summer, obviously we'll have ice cream, and then there is an increase of crime rate because probably there's less of food, or jobs, uh, unemployment and all that stuff. That might be the reason why these both are high, but it does not mean that these two variables are are in the relationship of a cause and effect. um, the next one is that correlation strength does not always mean that correlation is statistically significant. So correlation strength shows how closely the variables are related, and the statistical significance indicates if the relationship is due to chance, right? So a correlation can be strong but not significant if the relationship is likely due to chance. One of the reason for this is because of the sample size. If the sample size is too small, so it can show that it is statistically, it might show that it is statistically significant, but it's not. Also, like, we'll just talk with an example. For example, a study may find a correlation between certain medication and a decrease in symptoms of a particular disease. However, if the sample size of the study is too small or the study design is flawed, the correlation may not be statistically significant, indicating that the observed relationship is likely due to chance. Um, yeah, the next condition, it is always between -1 and +1. So, any expression of correlation, which is by correlation coefficient, it is always between -1 and +1, where plus indicates a positive correlation and minus indicates a negative correlation. So, probably we can talk about the relationship between hours of studying and exam scores. again. So, right, no matter what variables you measure, it is, you'll always measure, when you measure correlation, it is always between -1 and +1. It's just, it is almost reiterating of stuff that we talked before, but I thought it's necessary to show it again. um the scale, its scale is independent of the scales of the variables themselves. So this slide and the next slide is reiterating of the same thing, but I think it's just important to know from different perspectives that, no matter how the variables are measured, the way we measure correlation or express correlation is independent of the way the variables are measured. And then the next one is that it is standardized, the way correlation is measured, expressed. So it is always between -1 and +1. Again, I'm just reiterating what I've spoken before. Okay. So, like I mentioned before, correlation is only for linear relationships, but there are also nonlinear relationships that exist, where correlation, we cannot measure them through correlation, but then there are other methods to measure them. I'll just like briefly speak about the different types of nonlinear relationships that exist. One is quadratic. So an example for quadratic relationship might be the relationship of energy usage and temperature outside. So let's just say that the temperature is very high outside, it's very hot. So obviously our energy usage is also, it increases. And then as soon as the temperature decreases a little, our energy usage also goes down. And if the temperature becomes too low, it's very low, uh, then there might, the energy usage also increases again. So that's where you can see a quadratic pattern. And then the next one is exponential pattern of nonlinear relationship. This we can mostly see in molecular biology, or when we are seeing demographics, right? The relationship between the size of population and the rate of its growth. So it's very extreme and sudden, and that is when you can see this pattern of exponential relationship. And the other one is a polynomial relationship, where you can probably speak about the relationship between diameter of a pizza and its price. So it's not constant, it might increase a little, then it can get constant, and again it can increase further. So this is a polynomial graph. Even though this is not used in correlation, it's just better to know, as we'll be studying them when we study more on interpreting data. Okay, so here's a question. The scatter plot below shows the average traffic volume and average vehicle speed on a certain freeway for 50 days in 1999. This is how the plot looks like. So, can anyone answer the question on which statement best describes the relationship between average traffic volume and average vehicle speed shown on the scatter plot?
So as traffic volume increases, the speed decreases, right?
Yeah, okay. Here's another question. Miss O recorded the age and shoe size of each student in her physical education class, and the graph below shows her data. So, can anyone just say which of the following statements about the graph is true?
We don't see a trend.
Yes, that's the answer. So at last, we'll talk about correlation as a matter of degree. So the degree of association shared by two variables is indicated by the coefficient of correlation, which we'll not be speaking today, but if any other speaker who comes next could probably take it up. Um as we discussed before, a positive, the sign indicates only the direction of the correlation, not its degree, right? So plus is for positive correlation and minus is for negative correlation. Suppose we have an R value of minus 0.9, right? So it does not mean that it's because there's a negative sign. It does not mean that it's a weak. Uh, the degree of correlation is weak. It is a strong negative correlation uh, in from the negative view. And yeah, one of the correlation coefficient is denoted by R, which is mostly used by Pearson's correlation coefficient. And I just mentioned this because we'll be using it for the uh, research paper that we are going to discuss. Yeah, okay. So association between two continuous variables, right? So in Pearson's correlation coefficient, it is always between two continuous variables. And in that, anything below 0.3 minus or plus is considered as a weak correlation. And the value that is between 0.3 and 0.7 is considered as a moderate correlation. And the values that are greater than 0.7 is considered as a strong correlation. That's it. That is like the most basic elements of knowing correlation. And if anyone has any questions, they can ask.
I don't really have a question, but I just really love the slides you prepared and all the details you have put. It's amazing. Thank you so much for that.
Thank you. Oh, it makes me feel so good.
It was a really thoughtful presentation. Thank you so much.
Thank you.
Good job.
So, thank you, Ritik. Shall we take like a 5 minutes break before we start talking or discussing about the paper? Is that all right?